Okay, so today we're going to review some Chapter 5 material that you guys covered very speedily at the end of class last time, paying particular to alpha and beta, type 1 and type 2 errors for inference, and then we're going to be covering Chapter 6, which is new material, other than you've already done your summary, so not brand new. Okay, so the website, I'll be putting up the class lecture in our playlist for, so these are my playlists. Down here, there are other playlists that are other lectures, and over here on channels, there are other channels for statistics that kind of align with the content we're doing in this class. These are very good, well done videos on a lot of the things that we're doing, and they're really polished and professional, whereas my class recordings are really just on the fly. So the quiz I will be grading, the homework I'll be grading. Let's go over Chapter 5 quickly and then check that homework Chapter 5 question that you had. How's that? Okay, so there, I think did I say this before? This is the Chapter 5. Yeah, right? Chapter 5. Yeah, so what's the deal with causality? You need to be able to state that an association is a causal. One thing causes the other. You really should, the gold standard is to have an intervention. If you do an observational study, association does not equal causation. But a lot of times we want to study things that we can't do a randomized study for, an intervention study, like smoking. It would be unethical, thank you, to force people to smoke and not smoke. So the next best thing is to do an animal model. And then there's a list of all these bullet points, the things that we do with multiple studies to be able to build a mountain of evidence, a mountain of observational studies that connect things so clearly that eventually, when the whole mountain of evidence is collected, many, many, many studies over many, many years, that we can say holistically, yeah, it looks like there's causation going on. Did the snow get you? Okay, so this is where we talked about a p-value for the first time in class, right? So a p-value, if it's small, it says it's that we are very unlikely to observe our data, and the key here is assuming that the null hypothesis is true. So here's the definition of the p-value. So this is the one, and you can't shortchange this definition at all. I mean, you got to get the whole thing. P-value is probability, that's why the p comes from, probability of observing a test statistic or observing your data as extreme or more extreme. It's as extreme or more extreme. It's that tail area, that beyond C, the T. If, and this is the big thing, if the null hypothesis is true. So for all inference, we want to know about the whole population, but we can't get our hands on the whole population for a myriad of reasons. So instead we take a smaller sample. Our sample is the best guess at the population. But if we take a different sample, will we get the same results? Every sample that we could possibly take would give us slightly different results. So we want to know, the sample we got, is it so extreme that it casts doubt on the null hypothesis, or is it kind of just about the same where it's just random chance? So the justice system in the United States follows this phenomenon where innocent until proven guilty. So when we do statistics, we assume the null hypothesis is true until we have evidence otherwise. So when somebody is charged with a crime in the United States and they go to court, just because they're charged, we don't say they're guilty. And sometimes that's really hard as a member of the public, because you're like, everyone saw it. It's obvious they're guilty, but in the eyes of the court, they're assumed to be innocent until enough evidence is produced that the jury submits a guilty verdict. They never, ever, ever will have a jury say that someone is innocent. They are innocent by virtue of not being found guilty, but they're not proven innocent. We either have evidence or we do not have evidence, because we can never really know the truth. A lot of times in the past, one of the main forms of evidence was observers. What did the observers see? Because they pick them out of a lineup. They'd call up people that would tell their version of what happened. And over years, we have found, you know what? Human brains are very, very bad at recalling past events. They will have, you have 20 people watch the same car accident and then individually write down what happened. You'll get 20 different versions of what happened and who was at fault. Human recollection is not very good. So because of that, we assume they're innocent until we can get without a shadow of a doubt or get enough evidence. So that's the same thing we do with inference. We assume the null hypothesis. The null hypothesis is nothing going on. There's no association, there's no connection, there are no differences, nothing going on. And even if we're like, well, it's obvious something's going on, the statistics always assumes they're innocent, that there's no connection at all. Any differences we see are just random chance. If we took a different sample, it could be in the opposite direction, just random chance. So we never accept that. So we either say we have evidence against the null, or we don't have enough evidence against the null. So you guys talked about one tail versus two tails, and this is the question on the homework. So two tail, we find the critical value, the value beyond which we would reject the null hypothesis. For one tail, we put all of our alpha, which is usually 0.05, in a single tail. In a two-tail test, we divide it up. So it would be 2.5% in each tail. There is no difference in the math. You just have to decide which one you're doing. Now, which one should you do? One tail or two tail? Generally the answer is a two tail. Always do a two tail unless you have some very good reasonings why not. Because if you do a one tail test, people think that you are being picky, in that you're trying to overstate the results. We always do a two-sided because it's conservative, not because necessarily it's right or wrong. Like if I'm seeing if there is a summer slide in reading scores, like elementary kids, they monitor their reading all throughout the year. And so say by the end of first grade, their reading has gone up to here, then what happens when they go home over the summer? Then the next year they start right here, higher. Usually they lose some of their skills over the summer. Now some people might go up, but generally there's a summer slide. The null hypothesis would be that there's no change over the summer, that where they leave off one year is where they started the next year. And any deviation or difference there is just due to random chance. Now, we might only, if we're asking the question, if our research question is there a summer slide? That research question has direction to it. The summer slide means their scores go down. So a lot of times students will say, well, that we only want to know if their scores decrease. But that would be a one-tail test. But when we run the analysis, we almost always run it as a two-tail, allowing for decrease or increase instead of staying stable, because it's more conservative. If you ever try to publish a one-tailed t-test, you will have to have a lot of reason to back yourself up. Okay, so I did a workshop today which was on effect size and power analysis, and we covered these exact things on that slide for that workshop. So and whoever named these, type 1 and type 2 needs to be like drug into the street and shot, because I mean, who calls things type 1 and type 2? I mean, that means nothing. A type 1 is the first error that was talked about, and that's a false positive. This is a non-replicable study. If you do a study and you get an exciting, tiny, sexy p-value and you publish this article, news, flash, carrots cause cancer, p-value 0.00001. But do they really? Do carrots cause cancer? I don't
If they're
think
grown
so.
into mobile.
Yeah. Yeah. But if you publish something that says there is an effect, when really in truth there isn't, what's going to happen is somebody else is going to try to do the same research as you because they don't believe you or because they want to mount a proof. and they're not going to be able to find the same results. This is a huge problem in social science, false positive results that people have published, but nobody else can show the same thing happens in their own research. So this is what we usually want to reduce when we're doing inference. Alpha is the chance of observing data that extreme or more extreme if the null hypothesis is true, false positive. The second way you can have an error is a type 2 error, and this is a false negative. So this is where if there is a trend, but we can't declare it statistically significant. And this is usually the scenario for underpowered or really small sample data. If you have small sample data, say you only have 4 people in your study, they might show a big difference between 2 groups or 2 time points. There might be a big difference, but since you only have 4 in there, your p-value is not going to be significant. And that's a false negative. You can only say there's no evidence. You can't say that there's no connection, but you have to say I don't have any evidence of a connection. And a lot of times student research, thesis or dissertation will fall into this type of error because their sample sizes are not big enough. And that's usually due to time and money constraints because you have very little money as a grad student, unless you have a big grant that your mentor has, and you want to graduate in this lifetime, right? So type 2 is a problem. Now, which one's a worse problem? False positive or false negative? It depends. What if I'm doing a phase 1 clinical trial and I have 50 drugs and I want to know which ones to focus on? What's worse, a false positive or false negative? I'm going to try all these drugs to see if the patients get better. False negative? What? Yeah. What would a false negative mean? It means I would throw out a drug that was really important to keep. That's a bigger issue. What about a false positive? That would be I would keep a drug for the next round of testing that really is worthless. You don't want to do a lot of those, but of the two, if I'm doing a phase 1 clinical trial for screening potential treatment, this would be the more problematic thing. What if I am trying to figure out a reading intervention to apply to the whole state of Utah to all elementary schools? What's worse? It's going to be a new program. We're going to have to train every elementary teacher in the state, and we're going to have to buy new books for all the classrooms. Now, we've got a lot at stake. What happens if we put in a new program that really doesn't work? We spent a lot of time and money, and we've got nothing out of it. So both of these errors are important to reduce the chance of. Most of the time when we're doing inference, we focus on type 1, but type 2 is important as well. And whichever scenario you're in, one might be more important than the other. Now, what do we usually set alpha as? 0.05. So that means we'll have a 5% false positive rate when the null hypothesis is true. Where did 0.05 come from? Did Jeremy talk about that?
No, it's just arbitrary.
It is very arbitrary. So Sir Fisher, father of statistics, kind of set up this inference paradigm, and he said the p-value is the chance of observing data that extreme or more extreme if the null hypothesis is true. So if your p-value is tiny, that's evidence that something's going on. And people said, how tiny? And he said, well, small enough that it's not likely to be due to random chance. And they said, well, how small is that? He said, well, it depends on the risk of being wrong. And they said, yes, but how small? And he finally got so aggravated, he said, fine, for many situations, 1 in 20 is small enough. 1 divided by 20 is 0.05, and that's where 0.05 came from, was this 1 in 20 throwaway statement to get people off his back. And now we treat 0.05 as if it's this magical number, which it is not. And for power, so we use alpha 0.05, alpha the chance of a type 1 error, false positive. What do we use for the type 2 error? Beta. At least they got alpha with 1 and beta with 2. So beta is the chance of having a false negative. If we set alpha to be 0.05, what do we set beta to? Anyone know?
Is it 1 minus alpha?
It's not 1 minus alpha. That would be easy. It's usually set at 20%. That seems big, doesn't it? There is a connection between alpha and beta. They don't add up to 1, but there is, people say, well, why don't we make this 0 and this 0? Well, if you push these both to 0, your sample size you need is in the millions, pretty much the whole population. So that's not feasible. And so we kind of have to find a middle ground. Also, the smaller you make the type 1, it kind of makes the type 2 go bigger. If you try to reduce the type 2 more, it makes alpha bigger. Because there is a connection. It's not 1-to-1, but there is a connection there. So, and this is just another way of showing it. I don't like that one as well. So, assumptions. Assumptions of tests. Now, this is the first, in Chapter 5, we introduced the Z-test for one sample. In Chapter 6, we're going to do a T-test for one sample, and then independent groups T-test, and then we're going to do paired samples T-test, and we're going to do NOVAs. We're going to do a lot of statistical tests. Every statistical test grossly simplifies the real world. Always. It gives a very parsimonious overview of the really wild, crazy, interconnected everyness of us of the real life. So we're always simplifying it. The assumptions that pertain, every statistical test has a set of assumptions. And it is crucial that you know what things you're assuming to be true. Because I can almost guarantee that you're going to be violating one of those, if not all of those assumptions to a various degree. And you need to know if this is going to impact your results. Can you trust your p-value? Depends on how well you meet these assumptions. So you can plan on the homework and the test having questions about what are the assumptions and do you think you've met them. So for the Z-test, the first assumption is that we have a simple random sample. How often do we get a random sample? A truly randomly drawn sample. With human people, almost never. So this one we always violate to some degree. And you can't fix it with any stats. The best you can do is plan the best you can. And it depends on the scenario. If I am trying to gather a sample, hopefully a random sample of USU undergrads, what's a bad way to do that? Say I need 10 USU undergrad students.
Only psych.
Yeah, just stand outside one of these site classrooms and get the first 10 that come out and we'll pay attention to you, right? That's a bad way. What's a good way to get a representative random sample of USU undergrads?
A random number generator.
A random number generator.
Or like a list.
You need a list
But I said that
of
list
all
of
of them.
all of them.
Yeah, you got to get a list of all of them and alphabetically or whatever, number them from 1 to whatever, and then use a random number generator to pick them out. I'll tell you, we did that my first semester in this position. I had a faculty member here, and we talked to the registrar's office, and we told them we needed a sample size. I can't remember if it was 200 or whatever it was. And we needed to send this email to them to participate in our study. Go to this link and fill out this survey. So the registrar they wouldn't give us the list. That was not okay. But we gave them the email and how many we needed, 200, and they sent that email to a random sample of 200 undergrads at USU. Guess how many we got back? I think if it was 200, we might have gotten 27 back or something. Is that a simple random sample? We tried to do a simple random sample, but it ended up being not random who's came back. So what are some things we could do to get a random sample, to increase the likelihood? Incentivize, that has its own problems, but yeah. Oversample, so instead of sending it to 200, send it to 1,000, but still we're only going to get a small percentage back and they're going to be different. The ones we get back are going to be different than the ones who chose not to pay attention in the first place. In some situations, you can put things like incentivizing or going to each department and trying to get stratified, get 100 people in each department, somehow getting split up by freshman, sophomore, junior, senior, or in programs and try to get it as representative as possible. But this is something you cannot statistically test and you cannot statistically fix. You have to plan the best you can. And this is why I scream at people to come talk to me before they submit their proposal, because there are things you can do to plan up front to get a better sample, because statisticians always say garbage in, garbage out, but they use another word. Because if you don't have the randomness, or at least representative sample, there is nothing stats can do to fix it. Nothing, game over. We can run the stats and give you a p-value, but there's no way that that is true. So this is really important. It gets overlooked a lot. Your sample has to be representative. And if it's random, we can guarantee it's representative. If it's not random, we got to do more legwork. We always assume the standard deviation of the population is the same as the standard deviation of the sample. This is almost impossible to check or fix. We just set up an assumption. This will be true if we've done a random sample. If we've done a stratified sample, this might not be true. And so you need a more complex model, like a multi-level model. And we want the variables to have a normal distribution, but we know, even if our data is not normally distributed, if we take a sample, our central limit theorem tells us the sampling distribution of the average becomes more normal. So of all of them, this one's the easiest to kind of get away with violating. How do you check if data is normal? Plots are the best way. Histogram, box plots, QQ plots. You can do the standard skewness of their kurtosis and see if they're bigger than 2, positive or negative. There are also some tests. If you have small sample size, there's a Shapiro-Wilks test. If you have big sample, there's this other test. They're way too icky. Okay. So this is how did you guys go over this one? You got to tell me which point you went too fast. You guys hit this one? About how to write an APA. So notice number, mean, and standard deviation. Here they put them in parentheses, so they can use capital N, capital M, capital SD. And you always have, in a one sample, you're always comparing it to something. So that number you can put, or you could type it out, hypothesis value of SIX, or 6 in here. And then, so the summary statistics are in parentheses, but the Z and the P are not in parentheses, they're just commas here. Now notice, is there a 0 in front of that decimal? No, never for a p-value, but yes, for like a Z if it had. Okay, so did you guys go over this example? Anyone? Quickly. Yeah. Okay. So we're told that this is an anxiety score that has already been normed for a population. So it's already been psychometrically shown to be valid, reliable, and normally skewed, scored, and all this. It's a capital T score. Capital T scores always will have a center of 50 and a spread of 10. That's how the scores were developed. So here is a random sample of people in a town after the earthquake. If they were normal, if the earthquake did nothing, the average should be 50. You eyeball those numbers. What do you see about those numbers? What's the smallest one? There's 48. So there's one that's under 50, but most of them are well above 50. So the eyeball test tells you, there might be something going on here. It looks like on average it's bigger than 50. But to be able to succinctly say statistically it's higher, you got to do a test. So we always start with our hypothesis. If the earthquake did nothing, we would expect the average to be that norm's 50. Now, notice in the hypotheses, am I using X bar? No. Our hypotheses are always about the whole population. So our hypotheses will always use the Greek mu, never the sample statistics. It's always the population parameter. Now, is this a one-sided or a two-sided? A one-tail or a two-tail test? Two. Now, do we think that earthquakes decrease anxiety? But could it? They could go, whoo, that's over. It wasn't as bad as I thought. I guess so. Yeah?
I don't think so, but
yeah. Even though we think, based on thinking and the data, we really think that anxiety scores are going up. They're big, on average, they're bigger than 50. We always write it the two-tailed way, with that not equal to symbol. Now, sometimes some books will say this is H sub A, and sometimes H sub 1 for the alternative. Either works fine for me. I think your book usually does the 1. Does it?
The whole group does A.
The whole group does A. Yeah. We use 0, or we call it not, because 0 is the starting. So this is the null hypothesis. So you can say null hypothesis, or H naught, or H sub 0. Oh, sometimes they'll do H sub n. I rarely see that, but sometimes they will. So if here would be the distribution of all the population. In inference, we always work on the null hypothesis. So we always assume this null hypothesis is true. The null hypothesis says the center should be 50. Now this and the spread should be 10. That's the population distribution. But for the sample, we're looking at sample means. The center will still be 50, but what is the spread when we take the sample? This goes back to last unit. If the population has sigma 10, then the sampling distribution has spread sigma over square root of n. We need to know how many are in our sample. So that's why it's 10, the original spread, divided by square root of sample size. There happen to be 10 numbers here. So we get a smaller spread. Even if this was not normally distributed, this one would be closer to normal via the central limit theorem. Okay. Whoa, boy, there's a lot of stuff on here. And these colors are not showing up very well. Okay, so the first thing we do is we gather, after we have done our null hypothesis, we gather our data. We find the average. Is the average bigger than 50? Oh yeah, it's 58, that's bigger. But is it statistically significantly over 50? It's not 50, but we wouldn't expect a sample to be exactly 50. So is it far enough away from 50 that we say something's going on, or is it close to 50 and we say, nah, probably just random chance? That's what the p-value tells us. So 58 is on the upper side, so the p-value would be the chance of being this extreme, the observed data extreme, or more extreme in both directions if the null hypothesis is true. So you can do it as a p-value, or you can compare to a rejection region. They will get you the same answer. Now, in the past, 20, 30, 40 years ago, just saying fail to reject, p-value bigger than 0.05 or p-value less than 0.05 would get you into a publication. These days, they'll say things like, you need to submit Neyman Pearson significance values. What that means is they want the p-value to 3 decimal places. They just don't want to know, is it bigger than or less than the magical 0.05? They actually want you to give the 3 decimal p-value. But a lot of times books will teach this reject, not reject way because it's easier with a table in the back of your book, whereas this way you almost need a computer. So I kind of teach these together. They're not completely interchangeable, but you can do it either way. So we said we know sigma. The mean of the population is going to be approximately the mean of the sampling distribution. But the spread, we have to take the spread of the population, divide by the square root of the sample size to get the spread. Then when we do our z-score, observed average minus null hypothesis average over the spread. This z-score is 2.52. That's pretty extreme. If you look up the 2.52 in your table, you can find the beyond area. But if you're doing the not equal to alternative, the two-tailed test, when you look up the beyond area in the book, you must double it because this graph will always be symmetrical on the normal curve. If you're doing a one-tailed t-test, you don't have to double it. So here, so based on this, the critical value is 1.96. In a z table, we write the magical numbers. We did a z plus or minus 1 standard deviation. How much percent was under the 1 standard plus or minus 1 standard deviation? 68%. If we went out 2 standard deviations, we got 96. Yeah. If we want to get 95% exactly, you have to go plus or minus 1.96. It's almost 2 standard deviations. So this is beyond that. This p-value is going to be less than 0.05. So we can say, yes, there is statistically significant evidence that after the earthquake, this group of people has an increased anxiety level. Okay, so it's very important that there is a big difference between statistical significance, that's your p-value saying this is important, look at this, and practical importance, saying this is meaningful in the real world. So what if we found out that, let's see, what's the cancer rate in college students? What do you think? Throw out a number. What percent of? 1% of college students get cancer. What if we made everyone eat a vegetarian lifestyle, every college student, and we could reduce it from 1% to 0.9%? Statistically significantly reduce the cancer rate. Is that a practically, does that have any
chances?
What if it only reduced it 0.1%? It's definitely statistically significant, but is it important in the real world? Does it have practical importance? That's what this is getting at. So the way we measure practical significance is usually with an effect size measure. If we're comparing groups, a lot of times we'll use Cohen's d as a measurement how big the effect is. Not just that it's real, but how big is it? So the type 2 error comes up a lot. Sometimes we do a sample, or we gather a sample, we run a test, and our p-value is not less than 0.05. What happens to that study?
Probably never heard of it.
You probably never hear about it because nobody bothers to publish it, or the journals say we're not interested in publishing it. It's called publication bias. But is it meaningful?
Yeah.
A study that shows non-significance.
Yeah.
Yeah. It's important. For a long time, people thought these high-level voltage power lines caused cancer because people that lived around them got cancer more. Based on one town, they ended up finding there was something wrong with the drinking water that also just happened to be under that, just coincidence. Cancer happens in not just randomly spread in little clusters, because there's things in the environment. But it's not always the obvious thing. So even if you find association, it's not causation. But if someone did a study and showed that there was no connection, should we be aware of that? I say yes. So don't, just because your p-value is not small enough doesn't mean that you should ignore it. Okay, so here's the cancer data set. So we can use that site describe function to get measures of skewness and kurtosis to check the assumption of normality. Now there's only a kicker. You have to have at least two variables here or else it won't work. I don't know why it won't work with one variable. The site describe. But so one of the fundamental underlying assumptions is normality, and you can check it with the skewness and kurtosis. What was the best way you can check it though? Is with plots. So the histogram we've learned how to do before, right? And so the new one that we threw up here was the QQ plot. So the syntax is very much the same. You start with the name of the data set, you pipe it into ggplot. Now for a histogram, you just say the name of the variable. But for QQ plot, you have to say sample equals the name of the variable. And then here you say geom histogram. You can change the name of bin subhistogram. Here you say geom QQ. Does this look normal? What are we looking for when I say is it normal? Does it follow the bell curve? What do you guys think? Ish, very roughly. It is unimodal, it's kind of symmetrical. It's not perfect, but it's not terrible. Now remember, if it's not terrible here, the sampling distribution will be more normal, so we're okay. What are we looking for on a QQ plot for normality?
45 degrees long.
It will be a 45-degree line if the units are, lined up, but you want to see a straight line, diagonal line. How does it look? Not bad. I mean, you can almost, if you just blink your little eyes, you can see a very straight line there. We don't see this big S curve we do on bimodal or very skewed data.
When you get, so I remember hearing a reason once why you get like a step function. Is that a certain skewness?
Yeah, sometimes when you look at a QQ plot, you'll see like steps, flat parts of the steps. That happens when your measurement is discretized. Meaning, like if we were looking at age only to the nearest year, we'd have like in kindergarten or elementary kids, we have all the 5-year-olds, all the 6-year-olds, all the 7 and 8, and it would cause that to be kind of stair-steppy. So that's not something to be worried about if they're the steps going up there. What is worrying is if it's like S-curved. That's not okay. Or if you had 2 steps here and a step here and then another step over there, you know, if the steps are going up at a 45-degree angle, that's okay. And these are not perfect, but our assumption is that our variable of interest is normal-ish. Doesn't have to be perfectly normal, but normal-ish. So we said that there are the Shapiro-Wilks test to officially test this, because some people, their committee member might want an official test, which I hate. But this is how you do Shapiro-Wilks. Start with the data set. You have to pull out your variable of interest and do Shapiro.test. And it will throw this out. And it will say, ooh, what about this variable? Is it the assumption is that it is normally distributed, the null hypothesis. So if this is significant, it says that there's violations of normality. So this one's saying the variable age, it's normal. There's no significant violations of normality. This one over here, this is looking at the total world condition at week 4. Shapiro-Wilks says, yes, there are violations to normality. This variable is probably not very normally distributed. The reason I don't like these Shapiro-Wilks p-values is they're overly sensitive to small sample size, even though they're supposed to be better than the other one. So I never published them. I've never had anyone ask me, but I have seen students have a member of their committee ask for that. It's pretty easy to ask for an R. Okay. So you had a question on the homework for chapter 5, right?
Yeah, it was on like question 33.
Ooh, that's a lot of questions.
There are a lot of questions on here.
Six
That's
is that-
that's like
Chapter
in the
6
top.
is that way too.
That's not even halfway through the assignment. So.
Yeah.
33?
It's not that many in the book. In the book, it's like 10, but they're put in here where part A and B and C are all
Yeah.
separated out. So
So it's 5B question 1.
5B question 1. Here it is. That's really small.
So I get the Z statistic right, but when I do the two-tailed P, I got it wrong.
Okay.
And I'm just wondering if it's because I times it by 2.
What do you put?
Let's look at it on the board, shall we?
3.8.
That's what I put.
That's wrong.
Psychologist is testing a new anxiety drug which seems to have the potentially harmful side effect of lowering heart rate. For example, a sample of 50. Whoa. N equals 50. And often we use a capital N instead of the lower n if we're meaning the whole sample. I could have done a lowercase n, it would be fine. Student's pulse was measured after 6 weeks of taking the drug. The mean heart rate was 70. So this is the observed heart rate was 70 beats per minute. That's less than me. If the mean heart rate of the whole population is 72 beats per minute. Notice this was from the sample, so I labeled it X bar. This is talking about the whole population, so I'm using mu. It's important you keep those two straight. That's why I always write them down. And the standard deviation is 12. Now this is for the population. This is for sample. Okay. And we want to do, it says an alpha 0.05 and a 1 tail. What if it doesn't say how many tails? Assume 2. Always for this class and we always assume that it's 2 unless somebody tells us and gives us reason to believe that that's okay. On the homework, you got to take their word for it. Okay, and we got some formulas here. So, question 1 here, what is mu? 72. Okay, so even though there's a lot of questions, some of these are a little bit, hopefully not so, intense in our brain. Okay, so this next one, what's sigma? 12. What's n? 50. X bar? 70. sigma x bar. Ooh.
That's
We could write this as
12 over
sigma
the
of
square
the
root.
individual x's, sigma of x bar.
Isn't it? It's 12 over the square root.
12 over the square root of 50. Whatever that comes out to be. 1 point what?
697.
697. Everyone concur? Okay. If you go to 3 decimal places, you're almost guaranteed to be what I did. Do at least 2, never more than 4, but 3 is usually good intermediate. Okay.
Canvas rounds them to 4 anyway.
Does it round it to?
You can type 8 digits in and it'll round it for you to 4.
How nice of Canvas. Just does things.
It also adds a 0 before the decimal point.
Oh,
Yeah, it's true for p-values. You can't not, unless it's a text entry.
man. Technology. Okay. So this one you don't have to do anything, right? It just tells you what the hypotheses are.
No, you have to
we
choose
had
which
to
one is what.
choose.
Oh.
Yeah, it has a pull down to choose H.
Okay. So I should have put this in student view so I could see exactly how you see it. This is the preview teacher version. So which one are we going with?
H naught is the top.
H naught.
The top one? We want to know if it's greater than 72. Yeah. So Z. Now we have to calculate Z. And you're given these nice formulas. Isn't that nice that I added and then had Jeremy add the formulas for you? This is how the test is going to be. Either they'll be in there, all at the top, probably all at the top. But they'll be there somewhere on the test. Yeah.
Sorry, previous one. So the first one is H, no hypothesis, the early one. The before question.
Yeah. Which hypothesis was it?
The first one is H is 0.
Yes.
Yeah. The alternative hypothesis. Yeah.
So the alternative hypothesis is that it's going to be
The average is bigger than 72.
No,
No, opposite. It's less.
Less than. Oh yeah, because the drug is supposed to be lowering their heart rate, so it would be mu is less than 72. Now people get caught up. Do I need the equal bar on the less than or not? And it doesn't matter because it's not going to land on the average of 72 exactly ever in real life. So what goes on the top of our z-score? Our observed average minus the null hypothesized average. So we observed the average to be 70, but the null hypothesis tells us it would have been 72. So it's 2 off. The average is off by 2. It's not identical, but could it have been random chance or is it a meaningful difference? That's what we're asking. So it's important. What goes on the bottom? Do we put underneath it 12? No, we have to do the divide by the square root of n. Okay, so that's how you get your z. Oh, yeah, here it says two-tailed p-value.
So,
This is the question.
But up above it told us
Just to do a one-tailed test.
So I think the answer must be wrong in there. It's a one tail.
yeah.
So right here, this 2 should be changed to a 1.
Or the answer.
Or the answer should be changed to a two.
Yeah, or 0.238 is the right answer.
Let's go with the directions that told us to do a one-tail. So I can edit this right here. Watch.
I already submitted it, so
Send me an email.
okay.
So is that the answer? 0.119 for a one-tailed test?
Yes.
Okay. There. It's fixed for everyone who will see it in the future. Thank you. That's what we
There's
need.
another one like that too.
Ooh, there is.
Yeah, let me scroll. It's down farther.
So this one you were supposed to
No,
do.
42 is right, which is question 5B8. I did
5B8.
a two-tail.
Yeah, because it doesn't say in this question. It doesn't say anything about how many tails.
Yeah.
Yeah. So it should be a two-tail. Okay.
Question 5C3A.
5C3A. It should be done in, yeah.
Oh, but it does say, it says what is the two-tailed p-value, but my two-tailed was wrong. Maybe I did that one wrong. I
Okay.
don't know. I got 0.2.
Let's check.
I don't know.
What question number?
64.
64.
What did you get
Oh,
I
I
got
got point.
1.1605.
for the p-value?
That's
I got
63.
that.
Sorry. That was the z-score. I
Yeah.
got 0.246.
I must have done it. I got 0.246.
I got that
but-
the first time.
Well, let's go.
because
What's the
we
z-score?
had to, like, on our
1.1605 is what I got.
Yeah, I got 1.16 for my Z.
Okay, let's go back up here.
well, I don't-
Let's see. What was the average?
29.07. So yeah.
Oh.
Oh.
You know what? Oh, wait. I think I had a conversation last week after class with,
Jeremy?
with Liz.
Liz?
Because if this is the one I'm thinking of in the R, you do the test and it like only does the 85 count, and then like you do the next step of it and you do the one where you include the missing values, so you do the
Oh.
count, and then you do the next one, which is a totally different like function. So, like one was like psych describe and one was something else,
Uh-huh.
table or something, I can't remember.
Table 1?
But the first two round to one decimal.
Table 1
and
will
then
round to
the
one
other
decimal.
One, like the third one, which is the final one that you do for
Uh-huh.
that section,
Mm-hmm.
gives you
More decimal places?
2 decimal places.
Mhm.
So like I used for the X bar 29.07, but I think it was 29.1 if I'd have used the
If
first
you'd
one.
rounded it up, yeah. And that's why on the homework here is it gives you a margin of error.
Which-
0.25. So if you did 29.75, 0.075,
It was 0.07, so it's 0.3 off.
yeah.
Let me pull up my
So it
R.
would be wrong.
Yeah, let me pull up that assignment.
So it's 07?
I got 29.1.
Yeah.
Hold on.
Yeah, it depends on which place in the output you look. Whether
Yeah,
it rounded it.
But in the R coding, there was 3 steps to the R
Yeah.
coding because I think you wanted to show us what happens if there's missing values.
Yeah.
And all that, but the issue was that on the third step of that, I ended up noticing that they were rounded differently.
Yeah.
Wait, so Z was what? 1.16.
I got 1.19.
Yeah.
So
Again,
when I do the furniture, table 1,
let me open it in R so I can see what you're talking about so we can get everyone on the same.
P-value? Yeah.
So this is homework 5.
yeah,
Okay.
and it's around line 106.
Oh, that's unit 5. We don't want unit 5. We want chapter 5. Assignments.
I still got 2.46, but it must just be that difference in 0.12 versus 1.1.
Cancel.
That's one.
I feel like being off in the hundredths should not be.
It shouldn't be wrong. No.
So the
So-
p-value, though, is more sensitive to being off someplace else.
Yeah. This is why I like grading these by hand, because I could deal with that, but okay. Okay. I'm gonna run all of it.
Yeah.
So it's 5C3.
But the Z statistic we calculated by hand, right?
Yeah, but it's based on what you can pull out for the mean
Mm-hmm.
from the output.
Yeah, so here's table 1. And
So-
table 1's telling you 29.1. So it's only giving 1 decimal place.
But if
You can change it though. I didn't ask you to do this, but for inquiring minds, if inside your table 1 here, after you put the names of the variables, if you do comma digits equal, like I can do digits equal 4 or 3, and it will give you more. It only defaults to giving 1 decimal for compact tables, but you can say digits equal 3 or 4 or 2, and you can get more. So it is 29.07206, but it gave us 29.1 before.
Yeah, but if you go down,
Okay.
if you scroll down to the third output,
Yeah.
because the second output will give you a different stack. But
Yeah. So notice in this one, what's the sample size? 85. But how many people are in this data set? Not 85. There's 100. everyone has the stat quiz, but 15 people are missing the math quiz. Table 1 defaults to only including complete cases. So this is the average for the 85 that are complete cases. But this is the average for the 85 that did the math test. So this is where we have problems with real live wild data, is that always every variable has at least one person that's missing. So you need to be able to pick that out. So I'll do digits equal 4 here. Oh, I gotta close my parentheses in the right spot. So notice on this one, I did the na.rm equals false, and now I've got all 100. Did this change at all? Because there's still only 85 people in either table that have the math quiz, but now this score is different because in the table above, it used only the 85 that were complete. Here it's using all 100, even those that were missing the math quiz. Yeah, so the question is, should we be using 29.1 or 29.0706? It shouldn't make that much difference. In the real world, which one would we use? We wouldn't use any. The computer would use one that's even 10 decimal places longer, right? So this is a conversation that's not an issue in the real world, but it is pertaining to this class.
Yes, and well, see, and what I did is the next one down.
Use a psych
The
describe.
next one down, this psych describe, and it gave to 2 decimal places. And so I used those because I was like, well, that's the end. Maybe I'm supposed to use the output at the end.
Yeah, the nice thing about the psych describe is it will tell you that this variable has 85 values, this one has 100, and it doesn't restrict to partial data or all data. And so this number, 29.7, is the same. And this will match the one in the second table one, not the first table one. Because the first table one only did it for the 85 complete cases. Yeah. This is real life data issues. Which average do you put in your paper? I don't know. Depends. Okay, so and this is psych describe again, or yeah. So where we do the z-test on this, don't we? No, we don't. You're supposed to do it by hand, right?
Yeah, and I think that's what it is it's just the decimal places I used, and so
that's what
the range just wasn't big enough on Canvas to be able to include mine in it. So I'll send you an email.
Yeah.
Did you use the 29.1?
Yeah.
No, I used 29.07.
Okay, because that's going to happen to me too then, because I calculated off of
Okay, so what I need to do in here is I need to go in and say, put all answers to 3 decimal places or something.
Yeah.
Yeah, that's how I need to change it for the grading for the next class. Yeah. If you use either one, I will make it marked correct. I can override all the computer scoring. That's my tonight project, is to grade all those. Okay. And with not much more than 20 minutes left.
I have
Yes, another question.
number 50.
I don't see the 50, but
Oh.
I have the 5C.
5B, question 10.
5B, number 10, right here. Referring to exercise 8, suppose the mean is equal to 29.1. Where have we seen that number before? Regardless of the sample size, how large would n have to be for a calculated z-score to be significant? Okay, so in this formula, x bar is going to be the 29.1. Mu is going to be 28. Sigma of x bar is going to be 1.697. So we have all three. We have all 3 of these numbers. Oh, but this is based on a sample size of 10.
You have to come up with.
So we have z equals and then a fraction. On the fraction, we're going to do 29.1. It tells you to use 29.1, the 1 decimal, and then 28. And under here, what's the? It says referring to number 8. So let's go up to number 8.
We're gonna have to calculate a new.
Yeah.
So I think if I remember right, what I did was I went to a z-score, and I looked.
This should be.
I looked for a z-score that gave me a .01 two-tail,
Yeah.
And
This-
then I
yeah.
put that z-score into the formula.
Yeah, that's what you
figure
have
out
to do.
what that was.
So what's going to be done here is going to be 6 divided by whatever we decide the sample size should be. To be able to solve for this, we need the z to be over here. And this should be, we look it up in the table, like you said, a z-score with one tail and,
Two-tailed, 0.01.
did it say 2? I thought it said 1. I'm not reading too carefully. I'm still in vacation. Oh, a 0.01 level with 2 tails. So it's 2 tails, but alpha equals 0.01. Right. So this number on the side of this, we can get off the z table by looking up these two things. Now, if it's 2-tailed and alpha is 0.01, is 0.01 in one tail or both the tails combined?
Both.
This is the 28, we're at 29.1, and we want to know the p-value, which is the chance of being that extreme or more extreme, but 2 tails means in both areas. So this tail and that tail together have to be 0.01. So each side is 0.005, and your table has 4 decimal places for the area. So this one's 0.0050. So when we look up our z-score, this z-score, we're going to be looking for that much, half of the alpha in the beyond area. So let's see, where's our table? So let's see, 0.005. Is 0.005 exactly in here? No. 0.005 would be between these two. So our z-score is going to be between those two. Now, 0.0050 is exactly in between here. So you could say z is equal to 2.575, or you can round down to the lower one to be more conservative. I don't care which one you do. My general rule for this class is to tell you to do whichever was closer. And if they tie, go with the more conservative. So that would be 2.57. So now we have a mathematical equation that has numbers everywhere except for one letter, and you can solve it for that one letter. Fun stuff, right? Do you guys want to do that together? No, okay. All right, so that's how you would find out the required sample size if this was the mean and that was our critical value.
But,
Yeah.
Yeah, because why I'm confusing is, I don't know how can choose the both.
Yeah, which one to choose?
Yeah, because they are the
It's,
same.
yeah, the same
Yeah.
distance. And the good news is in the real world, you're not going to have to, because you're going to let the computer do it, and it's going to get it exact to 10 places. These choices, like, there's in between both of them, which one do I do? That's only for the homework, because of course you need to use the table. In the real world, the computer will give you it exactly. But we have a few of these use the table in the homework to see if you understand the concepts without using a computer. I'm sorry, yeah.
Isn't the conservative one the larger z value?
Oh, that would be the larger z value because it'd have to meet a higher threshold. But again, if you put it in between, I think that no matter which number you choose here, now, can n be a decimal number?
No.
No.
No. Oh, no.
That's good.
N, so what if you got n equals 30.8? What should you have your sample size be? 31. Because you should round up. What if you did all this and you came out and your sample size should be 99.01? What should be your sample size?
Should be 100.
You gotta go up to 100. If there is any decimal, you have to round up on the sample size. Because to get 0.01 of a person, you have to have the whole person. Because we're not doing fetuses. So I think that no matter which one of those numbers you use here, they're all round up to the same whole number. So which is why we don't get to concerned with that. Now, if we're doing averages and standard deviations, use the decimal. The only time I want you to not have a decimal is for sample size. That better be a whole number. Yeah.
Before we move on to number 6, can you say one more time, does a high p-value for the Shapiro-Wilks mean it's normal? Or the other way?
We don't say it's normal, we say that there is no evidence of violations of normality.
Okay.
It's one of those, we can't say it's innocent, but there's no evidence of guilt things.
Okay.
So in the Shapiro-Wilks, if you get a bigger p-value, you say there's no evidence of a violation to normality. Yeah. It's one of those where you want it to be non-significant because you don't want violations to normality. Because the null hypothesis is nothing going on, it's normal. So if you get a significant p-value, it says, uh-oh, there's violations to normality. Yeah, it's sometimes we want things to be significant, sometimes we don't. Remember, p-value is not, whatever the size of the p-value is not good or bad, it's just the facts. We don't have to be overzealous about one way or the other, it's just the facts. Okay. Does this one have, oh, this is a multiple choice one. Oh, it didn't show me the multiple choice, okay. All right, we're gonna use the last 10 minutes to go into the new chapter. Now, the new chapter is confidence intervals and the t-distribution, and what do you notice about the slideshow link? It's not there because I got in so late last night. I will link it. Right now, I got it off Tyson's website. I will put it up there on our link tonight, before I grade. So, this nice thing about this chapter is it flows very closely from the last chapter. So, the idea of a standard error, sigma of x bar, is we take the standard deviation of the population, divide by square root of n. That still exists. Our formula for the z-table, the z-score, that is appropriate for only for large samples, usually in the realm of hundreds, like 300. Who has a sample that's always going to be over 300? In the real world, it turns out we don't always have large samples. The math only of the z-test statistic only works if you have a large sample, because the central limit theorem is required for it.
The book says 100.
Yeah, 100, 300. They're all just kind of these vague rules of thumb. The idea is that it's large. If you have a small sample, this can be inaccurate. So what happened is there was, and I think the book talks a little bit about this, a certain man who worked for a beer brewing company, and he was in charge of quality control. Now, if you're going to sample the beer lots, are you going to want a sample of 100 out of each day's productivity? What happens if you're sampling 100 cups of beer every day?
So you're gonna
Not drinking it, just testing its pH and its concentration and all. It maybe tasting it, I don't know. But you can see there's a problem with a large sample in quality control, right? You don't want to waste all your product testing the product because you have none of the product left to sell. So in quality control and human subjects, this happens, we want small samples. And it turns out that the z-test is flawed for smaller samples. So this guy was like racking his brains trying to figure out how to adjust the formula to be right for smaller samples. And the thing is, the smaller the sample, the more that the skewness of the sample applies. The central limit theorem can't make it totally normal. It's just more normal. It's going to be still so much skewed. And the standard deviation of the sample will be smaller than the standard deviation of the population. And so we end up with inflation of type 1 error. For small samples, our type 1 error is going to be inflated if we use the z-test. In large samples, none of those are a problem. So here he is, William Gossett, working for Guinness Beer. He invented the t-distribution, which is an adjustment to the z-distribution. It's still a bell curve, but it's adjusted for small samples. Now he wanted to publish his work so he could get credit for this, right? You know, as professionals, we publish to get credit. But the brewing company said, we don't want our competitors to know about this. We want them to use the flawed test so that our beer is better than theirs. So they wouldn't let him publish it, and he fought him, and finally they let him if he did it under a false name, his publication, so that nobody knew it was about beer. So it could have been about mice or kindergartners. The competition wouldn't be keyed in on using it. So he signed it. His pen name was student, like a student of statistics. And so that's why it's sometimes called the student's T distribution or the student distribution. Not because it's pertaining to students, but because that's how he signed his publication letter. Because they used to send them in via letter, they didn't have internet at the time. So one key difference is this T distribution applies when you have a smaller sample, say under 100, 30-ish is prime, and it uses the sample standard deviation instead of the population standard deviation. And he was not working alone. Sir Ronald Fisher, Neyman and Pearson, remember I said Neyman, Pearson, p-values are the ones to 3 decimal places, and Galton, he was working with the big gurus of statistics in the day. And it works really, really well to use a T distribution when you have the smaller sample size, which you guys are probably gonna use all the time. So there are lots of things that are the same about the T distribution, and there are things that are a little bit different, T versus Z, the normal distribution. One big thing is this introduction of an idea of degrees of freedom. Now, for this chapter, I just want you to degrees of freedom means one less than the sample size. Just go with it. As we move through the chapters, degrees of freedom are going to come up more and more. There's more to it than that. I mean, this seems like a stupid math thing to do. Why don't we just use sample size? But it has meaning. Degrees of freedom have a lot of meaning. Degrees of freedom, so if we have a big sample size, what if our sample size is 500? Our degrees of freedom would be 499. This subtracting 1 doesn't make much of a difference. What if we have a small sample of 12? What's the degrees of freedom? 11. It makes a bigger difference for a smaller sample. And it turns out there's not just one T distribution. So there's only one Z curve, one standard normal curve. And so you have 6 pages in your book for it? The T distribution, there's not just one table. Because in the table it's set up very differently because there's a T distribution for 1 degree of freedom, there's a slightly different T distribution for 2 degrees of freedom, and on and on and on. So you have to use the table a little differently. So this is what the table looks like in your book. At the top we have the option, do we want to do 1 tail or 2 tail? What's the answer? 2 tail unless you have strong reasoning why not, or the homework tells you to do 1 tail. And you choose that by looking at the heading. You choose whether you're going to do 1 tail or 2 tail. And then here are the common alphas. It doesn't have all of the alphas because there are books that have full, huge tombs that people had to use back in the day before computers. Again, using this table, choosing which one, don't get too stressed out because in the real world, the computer's going to do the decimaling for you. Okay, so here is a picture, and the purple line here at the top, see the most peaked one? That's the bell curve of the normal distribution. What do you notice about the T distributions? The blue and then the dashed red. They're roughly the same shape, but they're a little bit squished. The T distribution, if you were to draw it out, looks almost the same as the Z distribution, it's just squished. And the smaller the sample size, the more it's squished. Squished in that the peak is lower and the tails are higher. It's flattened. So to use this table, you have to make some decisions. First, you have to decide 1 tail or 2 tail. Then you have to do alpha. What is our default? 1 or 2 tails? 2. What's our default alpha? 0.05. So we go to 2 tail, alpha 0.05. So we're going to focus on this middle column. Then you have to decide how many degrees of freedom we have. What if I have a sample size 10? Then we go to 9. And you come over here where alpha 0.05, 9, and you find out where they cross. This number, 2.262, that is your critical value. If you have sample size 10, and we're doing a 2-tailed 0.05 critical value. So if your t-score is bigger than that, positive or negative, you would reject the null hypothesis. Now in this one, we cannot get exact p-values. Sometimes our p-value, what if I had a sample size 10, and my t-score came out to be 3.0. see. Okay. So I was gonna see if I could draw on there. But, okay, so I can't draw on it. I know how. So make it easier to see. If I can find my pen. Yeah. I can't find it. Okay. We'll just have to use pointing. Find that pen. Probably left it at home. So if we have a sample size 10, we're on this row that says 9. If my t statistic, my test statistic is 3.0, it would fall between these two numbers. So if my t statistic was 2.8, my p-value would be exactly 0.02. If my p-value, or my test statistic had been 3.25, my p-value would be 0.01. But what happens if my test statistic falls between these two? The best we can say is that our p-value is in between 0.01 and 0.02 if we're using the table. The computer will actually spit out the 10 decimal places. So when you're using the table here to do p-values, your answer might be between 0.01 and 0.02. Sometimes that's the best we can do with the table. So let's look at the formula. So here's the t. What does this look like? It looks like the z-score. The difference is we're using sample standard deviation instead of assuming we know the population distribution. And then we have this degrees of freedom, which is 1 less than the sample size. Everything else runs the exact same way. Okay. Assumptions. The assumptions for the t-test, one sample t-test, are identical to the z-test. We assume that we have a random sample. How do you test that?
Normality.
That you have a random sample?
No.
Oh, how do we test that we have a random sample? That it's random. You can't. You cannot statistically test if it's random. It's like a trick question. So there might be a question on the test that says, list the assumptions of this test and tell how you would test them. And so assumption number 1 is that you have a random sample. How do you test it? You can't. You just plan really well, as best you can. Second assumption, the spread in the sample represents the spread in the population. How do you test that? You can't. And the last one is that you have a normally distributed variable. How do you test that? Oh, we have lots of options, right? We can do those plots. We can do skewness and kurtosis with the site-describe function. We can do that Shapiro.test to see if p-value is littler than 0.05, then that suggests that we have violations of normality. New stuff? Not really. Okay. So we are out of time, as always. I will do a recording of the rest of this. Let's see, what is there? There's an example to run through, which will be exactly the same as this example. The only difference is when we do the t formula, we'll call this t, and we'll have to use degrees of freedom to look it up in the new table. Here's some nice handy things. You can store, if you have a list of numbers, you can store it. What does that C do outside the parentheses? Combines or concatenates. So here's our list of numbers, and I'm going to give it the name X. And I can say, what's the length of X? And I'll say, you have 10 numbers stored in X. And I can ask for the sum, the mean, the standard deviation. So you don't have to do button pushing on your calculator. Kind of handy, right? So this one is all on the board, but notice the mean is the same. The standard error we divide by square root of n, that's the same. When we do our t statistic, that's the same. But now we have this degrees of freedom to look it up in the table. Okay, so let's see, confidence intervals, I'll have to do, and writing APA style. Okay. Now, in chapter 5, you didn't do any z-test in R, right? You can't do a z-test in R, but I know it's really. Well, you can do a t-test.
There is a function.
Is there a z-dot test?
I think that there is one in the book.
Oh, did I put one? For t-test, you can. The t-test is pretty easy. You say the data set, and you have to pull out the one variable and t-dot test. What does this say? Mu. So this is what we're testing. Is the average, the null hypothesis, is it equal to 165? This is weight. So we're saying, is the average weight 165, or is it more or less than that? And this is the kind of output you get. You get your t-value, your degrees of freedom, your p-value with a 0 in front of the decimal place. Might I point that out? And it gives you the confidence interval, and it tells you the mean. This sample average was 178.28, not 165. This is a higher average. Is it statistically significantly higher? Yes. This will always be a two-tailed p-value here. If you want to,
could you adjust it by putting in something? In the
you put
test?
alternative equals. Let's see, do I have R up? So you can come into your help panel here, and I'm going to type in t.test. And notice what are the defaults? Alternative equals 2-sided, less or greater. So it defaults to doing the alternative as a two-tailed test. If you want to change it, you would say alternative equals and then quote less. That would be testing, is the sample lower than 165? Or you would say alternative equals greater, and that would test the one-sided if your sample was higher than the mu. You're testing the alternative. And then mu, we're doing paired equals false. Later on, we'll do paired samples t-test, and we'll turn that on to true. Variance equal, we're going to work with that later, and by default, it does a 95% confidence interval. Okay. So I'll do a recording tonight, and then we'll bring your homework questions for chapter 6 Wednesday, and we'll answer homework questions. So I will make you a recording, and discussion board, I am back full time, okay? So chapter 6. Okay.